Hello, GAC. How are we doing today? Hey, it's Friday. First week back from spring break. Hope you're doing okay. Just a couple things that I want to mention to you. First thing is this: make sure you're continuing to stay up on all the podcasts and the homeworks. If you have questions, please feel free to email me, text me, whatever you need to do, and we'll go from there. One of the things that I want to make sure that I mention to you is that this lesson is probably one of the tougher lessons we're going to look at. We'll hit this more on Monday and even on Tuesday before our test next week. So just remember that going forward. If you need any help, anything whatsoever, next week I will be here all of those days before, and I might even be there after school as well. Hey, I've got a new member to my family. This is Emmy. Emmy, do you want to say hi? You want to say hi? This is Emmy right here. She's very, very sweet. That's why I've been missing this week. But she's stretching. If you see her, she's stretching there. But I'm going to go give her back to Mama, and then we'll get started with today's lesson. So 2.5a, make sure you touch base on the Algebra 3 GAC 2 website on 2.5a before going forward. All right? All right, I'll be right back. All right, sorry about that. I know it took a little bit of time. Thought a lot of you would appreciate seeing her though. Seeing that I'm actually not just skipping, but I'm actually just loving on my little girl, little Emmy. All right, Emmeline Faith Pemdas Johnson is her name. So just giving you a heads up on that. All righty, let's get this underway. I'm gonna go straight into our rational Descartes rule of signs. Now I will tell you this. Good night. This is going to take a little bit, all right? These ones it just is. It's a little bit tough. Remember when we talked about zeros? A lot of times we have, we try to be able to set up a problem for ourselves by being able to factor something out. But you'll see in a lot of the previous podcast stuff that I looked at this one by using all of this, the same thing, using this problem. I'm not going to do that one since we've already done it though. What I'd like to do is do the following. Now, in this one, remember before on section 2.4, 2.3, 2.4, we talked about how in zeros, that zeros, roots, and x-intercepts are very important. A lot of times in math or even in real-world problems, where the graph hits the x-axis determines a whole lot about the context or what the problem is talking about or doing. So that's very, very important. So in talking about the zeros of a polynomial, we have a couple strategies if we're not able to factor to be able to get this to where we find all of the zeros. But in doing this, we're going to be able to hopefully push you forward and not just leave you on an island, but help you in determining, hey, these are the ones, this is a good one to use and that sort of thing. So real quick, what we have is what's called Descartes' rule of signs. Right here, we're not actually figuring out the positive changes and negative change or positive values and negative values. We're just looking for how many positive roots and how many negative roots are we able to have within this problem. Now, in doing so, what we're going to do is we're going to first look at the positive changes. Now, think about this. First of all, this is the progression we go. We go from a positive, then to a negative, then to a negative, then to a positive. Now, you might say, well, what does that do, Coach? Well, again, positive, negative, negative, positive, okay? Well, this tells us actually quite a bit because what's going to happen is this. As I go from the first one, anytime I have a change in sign, you're going to let me know. So right here we have 1, no change in sign there, but a change in sign there. So there's actually how many positive changes? There are a total of 2 positive changes. Now, here's the thing. Hold on to that because what we're going to do is we're going to go down to the negative changes. Now, for the negative changes, it's pretty simple. It's a little bit different, but instead of putting x in, we're going to put negative x in for any of the x values. So we have here, okay, to the third minus negative x plus 1, okay? So look at this real quick. We've got negative x to the fourth is just x to the fourth, so keep that there. Negative x to the third would actually be negative x to the third, so negative and negative make a positive 2x to the third. Negative and a negative make a positive x and a positive 1. So as I look at this, as I go from positive, 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 there is no sign changes. So as I look at this, what happens is you know that how many possible positive roots are there. Well, in order to determine that, we go to the positive changes, and we note that there are a total of 2. And we go to the negative changes, and we determine that it's 0. But the problem is this, the 0 will stay the same, okay? So there are 0 negative roots. That helps us out quite a bit. That means if it crosses, it will not cross the negative side. Any negative roots, there will not be any within this polynomial. Now, as far as how many positive roots there can be 2, but then we have to subtract by 2 until we get to either 0 or anything that is less than 0. So we'll have 2, 0, and so there could either be 2 positive roots or 0 positive roots. Now, I know what you're saying, Coach, what does this do for us? Well, if I'm looking at what the zeros are, remember, zeros, roots, x-intercepts are all the same thing, and they're very, very important for real-world problems. Some of you will use this at some point where you're trying to find where this graph hits the x-axis. So in this, the possible positive roots are 2 or 0, and the negative roots is just 0. Okay, so let me go to this next one. Again, very similar. We can't factor this out. Even if we group together, that wouldn't do us any good. So what we got to do is the possible positive roots. So this will go positive to negative, positive to negative. So there's 1 sign change, 2 sign changes, and 3 sign changes. So there are a total of 3. Therefore, how many possible positive roots? It can either have 3 or, remember, subtract 2, 3 or 1. Now, if I subtract 2 again and be in the negatives, and we can't have a negative root, so you will either have 3 possible positive roots or just 1. Now, how many possible negative roots will I have? So this is where I plug negative x in. Okay, same problem, just plug a negative x in for all the x's to see what happens when I plug in our negative values. This would be minus 4, I apologize for being minus 4. So this one would be negative x to the third, so negative 3x to the third. This one would be x squared, so negative 5x squared. This would be negative 6x minus 4. So as I go from one to the next, it so happens, like the last one, there's actually 0 possible negative roots that are there, okay? Now, let's talk about this. What is a rational zero test, all right? Rational zero test. So that's Descartes' rule, okay? We call that Descartes, okay? Descartes' rule. On this one's a little different. We call this the rational zero test. We say state all of the possible zeros that are there. Remember, a constant is something that is the value in front of my exponents. Remember, exponents is anything with x on it, but the constant is something just a value. The lead coefficient is the value that's in front of my highest degree, okay? Now, in order to kind of figure this out, what we've got to do is to kind of figure out a couple things. First of all, our rational zero test is what we call P over Q. Now, that's just kind of a fancy way of saying that P would be my last value, where Q is the first value. So if I put in, let's say, 4, and you don't actually have to take the sign here. You can, but you don't have to. And Q is 3. So to find the possible roots, meaning what does that mean? The possible places where it crosses the x-axis or x-intercepts or zeros, whatever you want to call it, same thing. To find the possibilities, what we're going to do is we're going to find the factors of 4. So that's going to be, what 2 numbers make up 4? Well, that's 1 and 4, as well as 2 and 2, which we only need to put once. Now, what are the possible factors of 3? Well, that'd be plus or minus 1 and plus or minus 3. So as I do this, what I'm going to do is I'm going to find my possible zeros by doing 1 underneath 1, 1 underneath 4, 1 underneath 2. Then I'm going to do 3 underneath 1, 3 underneath 4, and 3 underneath 2 to get my possible zeros. So I'll have plus or minus 1, plus or minus 4, plus or minus 2, right? Because I put 1 underneath all. Now I've got to apply the 3 here. Then it's plus or minus 1/3, plus or minus 4/3, and plus or minus 2/3. All of these are what we call our possible zeros, meaning that these aren't the zeros of the polynomial, but it's a really good way to guess whether, a good way to kind of have a guess that's a little bit shorter than just 0 to infinity. So we have all of those values right there as our possible roots of that polynomial. Check out this one. Again, just like we did before, this right here is our Q. This is our P. So we're going to do P over Q. P would be -3. Q would be +1 because that's our lead coefficient. My factors on the top would be plus or minus 1, plus or minus 3. Factors on the bottom are just plus or minus 1, nothing else. So I have 1 over 1 and 3 over 1. So my possible roots are plus or minus 1 and plus or minus 3. And again, that means that those are the ones that I would use to guess in my polynomial. Where does that polynomial hit the x-axis? Okay. Side note, you could also factor that by grouping, but you don't have to. Just kind of giving you a heads up there. Okay. All righty. Now, what about this? Okay. Now, I will tell you this. This one on the test is going to be easier than what I'm doing right now. Okay. However, there will be problems where you'll have to do all of these steps. Okay. So there's 3 things that you need to know. Number 1, we're going to use Descartes' rule. Okay. So again, right here, you do not have to know every single part of this, but this is a good one. If you know this one, what I'm doing here, then you're going to be okay. All right. So again, these are just a couple of them. So let's do this one first. Descartes' rule. How many possible positive roots? Okay. Possible negative roots. All right. We're going to look at that. And then over here, remember it's P over Q, where P is the last, Q is the first, lead coefficient. Okay. All right. And we'll go from there. And then lastly, we're going to use synthetic division after that. Okay. So let's look at this. Possible positive roots. So let's do this one first. We go from positive to negative, positive to negative. So I have 1, 2 sign changes, 3 sign changes. So we could have a total of 3, and then we subtract 2 or 1. So we have 3 or 1 positive 0 solutions. Okay. What about negative? So if I plug in negative x in for the x there, okay, negative x in, I would get negative 3x to the third, positive here, minus 19x squared, because that, again, even power, minus 33x minus 9. So there's actually 0 negative roots. So that really helps us out because we know that there will be no negative x-intercept zeros or roots. Again, all 3 of those are the same exact thing, okay? Where it hits the x-axis is what we're talking about. Now with rational zero tests, we got our first step. The rational zero test is P over Q, where P is -9, Q is +3. So what are the factors of 9? Well, that's plus or minus 1, plus or minus 3, plus or minus 9, okay? All right, on the bottom, the factors are plus or minus 1 and plus or minus 3. So once I do this, I get 1 over 1, 3 over 1, 9 over 1. So it should be 1, 3, and 9. Next one is 3 underneath 1, 3 over underneath 3, and 3 underneath 9. So that would be 1/3, 1, plus or minus, that should be, and 3. Since I have these as the same thing, I don't need them twice. So the possible zeros that I have are 1, 3, 9, and 1/3 with plus or minus on the outside. But remember, we do not have any negative zeros. So that really helps us out here. So what we can do is finally our third step. So we got 1 and 2. To find all of our zeros, we just need to figure out what 1 is. Now, as I'm looking at this and I'm trying to just making sure. I just want to make sure I'm getting one that's a little bit easier there. Let's do, and in this problem, I would give you that, let's say x equals 3 is one of the zeros. Okay, is a 0, meaning that I could plug 3 in for here. Remember, on the previous one in long division, or in the synthetic division, if I said this, right, with all the stuff on the inside, I changed the sign. However, if I say x equals 3, you just take down whatever you see, you take that down there. Now the coefficients, values in front of the variable, we're going to plug in from the highest lead coefficient down. Make sure if you miss one, you feed that in. Okay, so we'd have 3, negative 19, 33, negative 9. So bring down the first one, which would be 3. Okay, then we multiply. 3 times 3 is 9. Add. Negative 19 plus 9 is negative 10. Multiply. 3 times negative 10 is negative 30. Add. 33 minus 30 is 3. Multiply. 3 times 3 is 9. And add. Negative 9 plus 9 is 0. Since this has a remainder of 0, we know that it's got to be a 0 or an x-intercept. To where now we have the remainder, the value by itself, the one with x and the one with x squared. So now what I have is 3x squared minus 10x plus 3. And I'm going to set this equal to 0. So I could factor this by doing the a times c method. But for me, I'm going to try to see if I can do it the long way here. To where, let's say, because this is negative in the middle, I'm assuming both are going to be negative. To where this would be negative 3 and this would be negative 1. Because I have to add to be equal to negative 10. You could check that, but I believe that's right. So I set both equal to 0. 3x minus 1 equals 0. And x minus 3 equals 0. Add 3, add 3. X equals 3. And x equals, add 1, divide by 3. X equals 1/3. So again, we looked at it before that there should be 0 negative solutions, negative zeros. And you're right. There's actually 3 positives, which mirrors up with Descartes' rule of having either 3 or 1. Okay. And you'll notice too that all three of these are underneath the possible zeros within this polynomial. Okay. Again, all 3 of these will probably have in a separate problem. However, if you understand that one, man, you're really on a good note. Let's say you understand one of the 3, 2 of the 3, whatever that may be there. This is going to take a little bit more time, and it can. We'll work through this together. Make sure you get up through 2.4 pretty good there, and then the rest of this we'll try to hit on 2.5b and more 2.5a on next Monday. Hey, again, thank you so much. This was great to be able to help you all out with this. If you have any questions, let me know, and we'll see you all on next Monday. Bye now.